Hello and welcome to the Superposition Guys podcast. My name is Yuval, and my guests today are Sullivan and Manish Singh, co-founders of memQ. We discussed their company's goal of developing a platform that is native to silicon for rare earth ion-based qubits with a focus on quantum communications, the need for quantum repeaters to extend quantum information transmission distances, the potential use cases for memQ's technology, compatibility with existing telecom infrastructure, scalability challenges, and much more. We hope you enjoyed this episode. Hello, Sean. Hello, Manish. Thank you for joining me today.
Hi there. Good to be here.
Yeah, thank you. I'm very happy to be here with you.
So who are you and what do you do?
So Sean and I, we started memQ, and we are currently I'm the CEO of memQ. Sean is the CTO of the company. And what we are trying to do is develop this scalable platform that is truly native to silicon for rare earth ion-based qubits. And the first application seems to be in communication.
And what would the product do?
So it's a set of products that that come together to give us this on-chip quantum repeater. So we need emitters, we need entangled photon generators, we need quantum memory, and these are the key components that will come together to get this quantum repeater. Really,
why does one need a quantum repeater?
That's an excellent question. Yeah. So basically, to send quantum information over long distances, the way that people are thinking about it is to use photons to send individual flying qubits through optical fibers, for example. And through an optical fiber, over a certain distance, photons just naturally get absorbed by the material, so just like losses of the fiber. So there is, in a classical telecommunications network, classical repeater stations, which basically can amplify or boost, the optical signals of normal telecom lasers. But because of the no cloning theorem in quantum physics, you can't just boost a quantum signal. So we need to come up with a quantum version of a similar repeater to sort of enhance the length over which you can distribute quantum information.
How long is that length? So if I have a station in Los Angeles that wants to communicate with a station in Boston, how many quantum repeaters do you think that it will have to go through?
So yeah, if you decide to send it over an optical fiber link instead of like through some satellite-based communication network, which people are also working on, we can use like quantum key distribution as an example, right? The sort of current state of the art is a few hundred kilometers over which you can send, key distribution at a decent rate before your rates really start to drop off. This is using things like twin field QKD. So if you're sending something over, 4,000 or 5,000 kilometers, and then you probably want some base station or repeater every 100 or a couple hundred kilometers or so in an ideal case. So tens or dozens of repeaters in that particular link. Yeah.
Right. The exact answer becomes it becomes a function of how good is your repeater. Yeah. So your repeater is fantastic. You can have a lot of them there and minimize your losses. If it's not that, if it's good enough, then probably something around 20 repeaters there.
Would it work on existing telecom fibers, or do you need a completely different fiber layout?
The way we are developing our technology, it will be fully compatible with the infrastructure that already exists. And that's one of the major advantages of the approach that we have taken. So in our case, I mentioned earlier that we are building a platform that uses rare earth ions as the qubits. The rare earth ion that memQ uses it's called erbium, and that happens to be at the heart of our telecommunication today. So the wavelength is directly compatible to what's called the telecom C-band.
Why do you need a quantum memory in that configuration?
Yes. So the pathway that Sean described earlier, right? So where you're sending from location A to location B, and A and B cannot be too far apart because there's this natural decay. You lose that information. So say like the distance between LA and Boston, let's say we divide it so that we put Chicago in between, just as a fun experiment. So LA to Chicago, you establish a connection. At the same time, you're trying to establish a connection between Chicago and Boston. Now, the thing is that the connection establishment sending of these photon loss is inherently probabilistic. So you don't want to do two probabilistic things at the same time and get what's p squared, right? P into p. What you want is you want to be able to establish a connection, hold that connection, and establish this while the second connection gets established. And this holding of that connection, that needs quantum memory, because quantum memory refers to this ability to store quantum information.
It sounds like the LA to Boston example would require dozens of repeaters, as you say. So you must be thinking about an easier use case before a major telecom deploys your repeaters sort of network-wide. So what do you think would be the initial types of customers that would use your product?
So I think, yeah, that's definitely, instead of thinking about wide range distribution, you typically think about even classical telecom networks as having local networks before going to the wide area networks. So one area that I think is particularly interesting is even at the level of, let's say, like a single data center where you have multiple quantum components, QPUs operating relatively in close proximity to one another, as well as classical computing hardware. So doing sort of local area network connections over sort of maybe, let's say, hundreds of meters between devices. That's I think a very key initial milestone. The other piece there is even over local, like shorter distances, there is a need to be able to send data in a secure fashion between two places. So let's say you can encode the data using quantum physics as a means to send the data in an unhackable, or at least a way that could be detected if someone is eavesdropping, just using the statistics of quantum entanglement.
Do you envision the product to be a chip that would be integrated into someone else's device, or is it a standalone box that would connect the endpoints?
Right. So, yeah, in its first iteration, the way we are developing our technology, so it works directly with the current silicon photonics platform. So you would have a photonics integrated circuit that could sit inside a cryostat or a cryostat-like box, and it could provide those capabilities at that point of use. In subsequent iteration, we see this becoming a self-sufficient plug and play kind of option, where you can insert standard optical elements in there and interface with it via software and get the desired outputs via the ports.
Do you see that as an interconnect mechanism between, as people try to scale up? I mean, some vendors say, oh, we're going to have a 500 qubit chip, but if we need to scale to 5,000, then we're going to need 10 of those and somehow interconnect them. Or is that solving, is that using a big solution to solve a smaller problem?
So if I understand the question correctly, it's like the way we are approaching it, is it something like that? Will we have an interconnect like problem? Okay. So the way we are approaching it, we are using these nanophotonic devices to create this photon and atom interface. And the individual footprint of these devices, it's very small. It's less than 10 microns square, right? So in principle, you could put tens of thousands of these devices on a single chip. Now, the photonic activity is what's actually doing the computation. So the qubits, they serve as sources. The qubits, they serve as memory. The actual compute is happening via these the photons themselves. So that way, we see the platform itself as inherently scalable, in the sense that you can bring more and more qubits onto the same wafer. And the fact that we work with the standard silicon on insulator wafers helps with that point. But that said, because what we are trying to make, it's a network product, so connecting many of those isn't going to be a problem. Like if we can't connect multiple of our products, then we can't really make a network, a network of quantum repeaters. So that's kind of the advantage that this particular platform brings for us.
Tell me a little bit about the company. When did you get started? How large is the company? Where is it located? How is it funded? Anything you can share?
Yeah, I would love to tell you about that. Right now, we are at 10 people, and that includes six of our members are full-time members. They're PhDs from some of these top universities in the nation. They bring in cross-cutting capabilities in nanophotonics and atom light interface, in quantum dots and rare earth ions. Now, that team, it's located here in Chicago. And the reason we are in Chicago is because of this very vibrant system that University of Chicago, Chicago Quantum Exchange, the UIUC, like all these major research organizations, Argonne National Lab, they have been able to build out here. Our company, it started as a spin out from University of Chicago and Argonne National Lab. That's where some of the work that Sean and I did kind of led us towards that. Right now, we are funded through DOE via a program called Chain Reaction Innovation that allows us to leverage some of the DOE capabilities in order to perform some of the work that memQ is doing. We have also closed our seed round. That happened earlier this year, and we were able to bring in about $2.5 million in VC money to help support that effort towards prototype development. And we hope to continue building and continue expanding in Chicago.
Where are the chips manufactured?
Right now, as we continue the development, we make these chips in-house, as in the clean room at Argonne is where the prototype development is taking place. At the same time, we are exploring runs at two of the leading foundries in the US, two of the leading photonic foundries. And we expect our first tape out to happen before the end of the year.
Are there export restrictions on these kind of components?
That's a very interesting question, in the sense that we do anticipate something like that happening, but we're not aware of it. But regardless, we are being very careful, because we do work with the national labs quite a lot. We do interface with some of these other areas that are more sensitive to things like that.
As co-founders, what keeps you up at night? professionally? Maybe first Sean and then Manish.
Sure. Yeah, I think, I think because we're here in a national lab facility, we're using shared tools, things like that. There are certain things that are like out of your control in terms of having ownership over the entire process. That's, I would say, a minor concern though, generally. But yeah, I think kind of to like your point a little bit about the export controls and things like, I think that's an area that's getting a little fraught right now. This trying to understand how all of this quantum technology is evolving in the greater global environment, I think is a really interesting and really interesting area, let's say. I don't know, Manish.
My fears are a little more tangible in that sense. I primarily like it's it's about our capability to find that product market fit, really. Like, so if basically the ability to leverage that first use case, bring develop customers in that area, see widespread adoption of the technology. That's what we worry about a lot.
And hypothetically, if you were able to have dinner with one of the quantum greats, dead or alive, who would those people be?
I would say Bohr. I think, being right there at the sort of father of quantum mechanics, I think that's a very easy answer for me. Also, having just seen the movie Oppenheimer, I thought that was very cool to see all of the physicists that they portrayed in that movie, sort of reinvigorated that desire to try to meet Bohr. Yeah, that would be really cool.
Right. For me, that would be Fermi. Fermi, because like by that till the time that controlled fission experiment was done right here at the University of Chicago grounds, right? It was an entirely theoretical concept. We're kind of at a similar position with quantum, right? In 1942, when they did that splitting of the atom, in the sense that everything is kind of sort of proof of concept, everything is there till that large scale entanglement distribution is actually there. We're not really there. And until that's there, we don't know what we can harness that capability for. Is it going to be something as useful as, say, power plants? Is it going to be as useful as, say, a radiation therapy? So that would be fascinating. And to like get his perspective on seeing, his tech evolve over 20 years till by the time of his passing. It would be a fantastic conversation.
Wonderful. Sean, Manish, thank you so much for joining me today.
Pleasure to meet you all.